So sorry, it's me again. So static analysis in OCaml, but not for verification. So Flambda 2, as I mentioned earlier, is an intermediate representation inside OCaml. So, and that's a path where we do static analysis to know some things about the code to optimize it. So that's a work that we do at OCaml Pro with Gen-Street, and mainly, well, Mark Shinwell and Leo, but many others. So why are we making Flambda 2? Well, because we can, and because there were limitations in the previous versions. And I won't go too much into detail because there is a talk tomorrow about that. But here I'm going to describe how we accumulate, manipulate, and find information about the code for the Flambda 2 simplifier to make it know things about the code itself. So the constraint, which is not simpler for a static analyzer in general, is that the code is modified at the same time as it's being analyzed, which is not the kind of thing you see in verification, and makes it could make everything more difficult. But since we have that constraint, we implement everything in a pure way, and then that's quite okay. So it started as kind of an ad hoc analysis, and it evolved. We called that a type system at some point. In fact, it's really an abstract interpretation, so, well, now we call it that way. So the simplifier is something that traverses the code, accumulates information, and then reconstructs the code with differently to make the code better. So what do the analysis expose to the simplifier is quite simple. We have creation and deserialization of an environment. So environment is the abstract domain. And then we have updating function to add information in it. And basically, we just add properties. Then we can meet as an abstract meet, or join when we have different branches going to the same point. And then we can clean it. So that's for updating. And then for looking at it, well, meet is for updating, but is also a way to query the domain. Because basically, you can meet a property with the current domain. And if it's bottom, then that property doesn't hold. So that's the basic function that we need. In fact, usually it's not fast enough just to meet. So we have faster versions that are less precise, but are quite useful often. Because, well, we need to compile Gen-Street code base, and if we're not fast enough, with 40 million lines of code, apparently. So, the difference between verification and compilation for an abstract domain. So, from high level, not that much. We have an abstract domain. We need to accumulate data on it. But the main difference is what we expect in terms of precision into the domain. Basically, we often need to be faster than the verification domain. And so that's one constraint. But on the other hand, if we are bad, it's not that problematic. In a verification domain, if you have something that is top, then you don't know anything. You just know that your program don't verify your assertion, or verify your assertion, but you don't know anything. In our case, it's just a bit slower, maybe just in a local case that don't matter that much. So we can basically just don't consider part of the language that are not going to be amenable to optimization, and concentrate on the parts that might be a lot simpler, where you can do optimizations that matter. But on the other hand, if we have information loss, the generated assembly is going to be different. But you need to look at the generated assembly in some way to know that your domain is not precise enough, or to the intermediate phases, but the user usually is not going to notice it. So, what are the kind of properties that a compiler needs to know about values? What is useful? So, the basic properties that we want are numerical constant in general, because that the domain is going to be used for constant folding. So, anything that is constant is easy to track, and we are going to track it. But we want a bit more. So we have some information about the numerical constant, but also about blocks, to simplify access to blocks and to basically avoid access to blocks when it's possible, and to remove allocation of blocks, because allocation are quite expensive. Well, not directly expensive, but when you accumulate a lot of allocations, that's expensive, and if you can remove it, well, that's good in general. So we want to simplify function, but also we need to find functions. If you don't know what is a function and which function it is, you're not going to be able to specialize function calls as direct calls, and you're not going to be able to inline. And specializing to direct calls is very important because indirect calls are quite expensive by default. And well, if you know things about variants, then usually you're going to be able to detect some dead code, dead branches in if, and that's a good idea to remove it. And with a few more information, you can know things about values precisely, and you can do some kind of unboxing where you don't need the user to tell you about the value to be able to unbox some things. So what does the domain look like? So the values in the domain are for numerical values, just small finite set, simple. It's mostly simple, but because that's most of the time that's sufficient for optimization, and we don't need that much more. So blocks are kind of the most important structure where we need to be a bit precise. So we only track precise information about immutable blocks because that's simpler. And the OCaml memory model in general would make it quite harder to be able to do a local analysis that says anything about mutable values. And then we track the size of blocks with the contents, and yeah. And closure, we need to know which closure it is and the contents of the field. So basically, it's the same structure as blocks. Yes, and relational information about everything. So blocks, what I described is kind of a shaped domain. It's a very simple shaped domain, but it's a shaped domain, where we have two kinds of shapes that can represent block. They are complete shapes that usually arise when you allocate a block or when you take information from the type checker, where you know that a block has a specific size, can have a specific tag, and maybe things about what is inside the block. But when you do a get field, access a field in a block, you only know some partial information just about that field. And the size of the block is bounded by the field, but you don't know much more. And of course, we can do mid between both. So functions. Function, basically, the representation is just the code of the function. When we can actually inline it. When they are too big, we just drop the information. But we can also capture some information about the semantic of the function. Sometimes that's useful. So closure, as I said, they are like blocks. They contain functions in some kind of indices, fields in other kind of indices. They are kind of the same thing as the integers you use to access a block, but just for convenience, they are not integers because when you want to remove them, you don't want to renumber the fields. So, if you have just a naive domain just describing that, which basically is the case of the old version of the compiler, you can do quite a lot of things already, but you're missing some information, and you're not going to be able to track the information about one of the most important kind of values in OCaml, which are variants, the type definition of different cases. So to be able to represent that and have information in that, you need some kind of unions. And unions, if you don't do that in a smart way, in an abstract domain, that can be quite expensive, that can blow up quite quickly. So we restrict our unions just to some specific cases where we can discriminate quite quickly between the case of the union. So those types, it's okay, we have a union to represent that, but something that arises basically from a GADT, you can't produce a case like that without a GADT, where you want to do a union between an integer and a string. We are not going to care about that. It doesn't happen often enough in a situation where it matters for optimization to be able to represent precisely that, and the cost to be able to analyze that compared to the benefit doesn't justify it. So it's going just to be top. So as I said, we have relational information, which are mainly aliases that are useful to track the relation between variables and fields of stuff or other variables. So if you look at that example, we have two variables arguments to the function. We produce a block which contains that, and we extract the fields of that block. That's easy to optimize into something like that, because we could find that the alias that x is the first field of block, y is the second field. We can remove the access to the block. Then by removing the access to the block, we don't need the block anymore. We can remove the allocation. Can just do that. There are more complex cases where if you have relational information, you can also discriminate branches. Here, the block has twice the same field, so we can know statically that the last case of the match is unreachable when we do a meet on that case. I'm not sure that matters that much, but since we have that anyway, well, we can represent that. So to be able to track something like that, we have an aliasing domain, and that domain is a must alias domain. We say when two variables are the same, but that doesn't say anything about may alias or must not alias. Basically, usually may alias is important to optimize mutable code, to say that when you mutate something, it's not going to mutate something else. We don't care that much about mutable code, so, well, we don't care about may alias in general. So to store all those things, we store them in an environment that we propagate through everywhere through the code. So basically, an environment is a map of variables to an abstraction, an approximation. And we can do meet on given an environment and types. We can meet the types under that environment and enrich the environment with some new properties. So imagine that kind of code. If we propagate the environment through this, you will see that at the beginning, we start by knowing not that much, but since it's OCaml, we can find some information about the type of X. So X here would be alpha pair, and that couple. And in that, if we know that, we can produce an approximation that says that X is something at the beginning of the analyzing list of the function. Then when we bind the Y variable, that Y variable, we are going to extract it from the X. So we are going to remember the alias that it is something related to the first field of X. Then in the first branch of the match, we want to know in some way that it's related to the first field of X. We we discovered that y was a, then we want to be able to find that first field of x is the same thing as a. And to be able to do something like that, the basic way to describe it is to have a reduced product in, between the value domain and the alias domain. So a reduced product is kind of, you have two different domains, and you want that we implement independently, and you want to make them communicate. And when you do a meet or something like that, you try to propagate every information from one domain to the other. So in general, implementing reduced products are quite expensive or even sometimes impossible. So we don't do exactly that. We do an approximation of the reduced product in a strange way that we will see a bit later. That is quite more efficient. So the most important operation that we can do on our domain is a meet, which is used to query the domain and introduce values in the domain. So meet happens below an environment, and have two types that we meet in that environment. So to speak about that, introduce a few notations. So the types are the things that we are able to represent. So the naive things, top, bottom, not very interesting. So we can also have things that say this type is an alias to the variable x. That's closures. We won't say much about it. And that's the blocks, where we can put in unions. So we have different cases where it can be blocks or integers, or the top of integer. Not very interesting. And with blocks, you will notice we have some things that are extensions that we will speak about later. And close to that, we have the environment, which is a set of bindings to types and set of aliases, which are unions of variables that are supposed to be the same. So the code is that environment I represented as yellow in the slides. So the interface of the meet, as I said, so it's the environment, two types, the meet, and then we have a result type and a result environment. A naive meet is any environment you meet two types that are incompatible. So a block of type A, but we don't know the contents, type B, then it's bottom because, well, that's incompatible. But if you have a union and you meet two things that are incompatible and things that are compatible, then you keep just the compatible part. It's a pointwise union. You meet every part independently, but in practice, since all the things that you can actually represent in the union are always distinct, it's quite efficient to do that union in general. Here, we can also meet known tags to blocks where we don't know the tag, but we know the content. Then you know the tag and the content. And that's to show that the meet, when you implement it, it has to be in some way a fixed point, where you discover that two things have basically the same shape. Then you can, like a type checker, say that you push the constraint below, and you have to check below. Well, top and something is going to be the something. When you have aliases, the meet is a bit more complex. It's not just values. So if you have an environment where you don't know anything about x in the beginning, you meet a type that says it is an alias to x, then you're going to discover that x in the environment is that new information. Quite easy. But sometimes there was something that you knew about x, then you have to push the meet inside the environment and continue that. And that one is to demonstrate when you have something a bit more complex, you meet aliases between them, then you have to propagate that a bit further in the alias domain. Here you have two representations of the type. You meet the aliases, then you have to find fetch in the environment the actual concrete representation of those types, and say that you create a new meet between them, and you should choose one variable to be the canonical one. So here, y becomes the canonical alias for the set xy. So we return y now, and you say that x is equal to y there. So now, whenever we look at x or y, we will know the same information about those types. Yeah, I will skip about that. It would be. So if we, too much details. So environment extensions. So we have something that is a bit complex that we can store inside blocks or alongside functions, which are basically small sets of environments that we attach to a domain of a value. That is quite useful to describe complex structures. So when you have a function, for instance, we can store some basic summary of its semantics as an extension. So basically, that function returns a pair of things that are aliases to its arguments. So we say that we can say that in the type. So extensions can be attached to anything that can be part of a union. So for instance, we can encode the isInt or getTag primitive in the compiler as an extension, and that's quite useful because that allows us to discover things about the value related to the value of a Boolean. So the isInt primitive is something that isInt of x tells you whether x is an integer or not. So you just create the value when you evaluate the primitive. You store the union in the environment, and then when you do an if of that Boolean, in the two branches, you are going to know that in one branch it's a zero value, the false, and the other one it's the true value. And you will discover alongside that if you have only one case of the extension, then you can put every information from that inside the environment and then rediscover things about a different value. So that, that's the example which I said, where we discover here that when we do that meet, we remove part of the type, and when we remove part of the type, then we have the right to propagate the extension there and rediscover that that is more precise. So that's quite useful because that allows to destruct the blocks as the actual block and properties about the block, and don't implement inside the compiler a match on the block, but only match on single integers, and that limits the size of the intermediate language. So that kind of extension is quite powerful. We can encode things that says a lot of things about values. So for instance, that's not obvious, but if you have that in your environment, that's equivalent to bottom. But to be able to discover that, we need to test all the cases independently. And that's going to be expensive. If you do that in general, that's going to be NPR'd. And you don't want something NPR'd in your compiler. So basically, we don't try to look at the content of extension before actually having a single case in our unions. The other side, so we had the meet. We need the join to be able to produce things outside of merging branch. So when you have a if at the result of the if, you need to put something that is a join. So meet what's on types. Join is an environment. Since the environment basically represents the flow of information inside the program, you have that represents the flow of values, and you have to join the environment. So the join, quite simple. If you join things that are different, then you join the thing independently. But if you join things that are related, then we push the join below. So that's some place where we lose precision. But, well, if you want to do some abstract interpretation, at some point you're going to lose precision sometime. So join of aliases is another place where we might lose precision sometimes. If you join aliases where you have values linked to those variables, then the result of the join is something that is going to represent the join of the values. You don't know anything anymore about the aliases anymore. But you can still know things about the aliases if you join variables that are supposed to be aliased in the original environment. So those were examples of join on the types. And joins on the type are useful to implement the join of the environment. So to join environment, basically you have to find every constraint in both environments and join them independently. So that's quite expensive if you do that naively. And you don't want to do that naively because environment can be quite large when the code is quite large. So to improve that, we try to find the smallest part that is actually different between the two environments, and then we join just that and we meet that to the rest. Just to say, you might be surprised, but we don't have fixed pointer widening because we don't need. And yeah, conclusion. Yeah, that's in production at Gen Street. Apparently they are happy, and you can try that if you want. And yeah, if you want to do that for your ML, I think that's going to be compatible. In general, there's basically nothing specific to OCaml. Because we don't have fixed points. No, but why don't we need fixed points? We could need them. It would be too expensive to do that properly. And our domain would be really hard to check for inclusion. It's quite difficult. We could have some tricks to find a post-fixed point and find stuff, but not that easy. But it would basically be too expensive, and we want to find properties about the values. So there are things for which fixed point is useful for us, and we have something separate that do fixed point on specific properties that are quite easier to do than an abstract domain. And we use the result of that to inject back as specific aliases for the abstract domain.
Just to confirm, I mean, you're planning to put it in a Flambda when it's implemented, or it's already?
It's already in a Flambda 2, which is in production at Gen Street. If you want to try that, it's in the OCaml Flambda repository.
Oh, okay. So it's so it's already implemented. It's not in the main line, but it's already, so you have the experience of okay, great. Any more questions? Okay, let's thank the speaker again.